lung healthy or diseased. So basically, I'm just classifying some X-ray images into the healthy classes or diseased classes, right? So we're just going to do a little presentation 101 here. So just some few quotes. The co-founder of one medtech says that there are many hidden patterns in cancer data, right? And because of how hidden these details can be, always machine learning could come and leverage. I mean, but what's important is realizing that machine learning is not going to replace the role of humans, right? But rather it's going to augment what they're doing, right? So I've heard a couple of people, well, some came to me asking, so what you're doing, are you sure you're not going to take us out of the consulting room? And I was like, no, I'm definitely not going to take you out of the consulting room. In actual sense, I would even need you to help me label my images before I can even train my models. So far from that, machine learning is not going to take the role of any human. It's rather going to augment their roles and then help them even take on higher level decisions. Yeah. So what is it about X-rays that we look out for when we see a chest X-ray? So I'm just going to give a little, do a little discussion on chest X-rays just to help you keep up with me when I and when we are testing the model, you would want to see if my model is doing great, right? So at least you should be able to see if the chest X-ray is showing some pathologies or not, right? So this one here is a healthy X-ray image. That's the figure A. This is a healthy X-ray image. Now, what you'd be interested in picking out when you're looking at a chest X-ray, you look at the lung fields. So this dark portions here, and then this side. So we're looking at the right lung field and then the left lung field, right? So usually places that are filled with air are translucent, and those ones would be darkened, right? So all the dark patches here means we have air over there. And the ones that are radio opaque, that's the radio waves are not able to penetrate, those are marked as white structures. So all these are white structures. So in actual sense, this is one of the major blood vessels in the body called the aorta, right? And this is our heart right here. Yeah. So this is a very healthy chest X-ray. But when we look here, just compare this with this healthy one, you can see that this is very radiolucent. The right lung field is radiolucent, but we have a structure here that I've bounded with the red circle here. Now, this looks like a foreign material in the chest X-ray. Now, this could either be a pus or clot or anything. It's an infiltrate. It's something foreign to the lung field. In natural sense, all this should be filled with just air, right? But we have this mass right here. So this is picked up as a white structure. Now, these dots and lines you see in here are actually electrodes. I think this person has been kept on an electrocardiogram, right? So these are just the electrodes. And for this, just have a look at the heart, this part. We realize that this has taken so much volume. It's occupied so much area of the left lung field. So you can see that this heart is actually enlarged. And in the medical term, that's called cardiomegaly, enlargement of the heart, right? So this is a disease condition. And then we also have some mass or an infiltrate up here. If you juxtapose that with this, you just have the darkened region. That means this part is translucent, but looking here, you can see that this has some mass or infiltrate in there. Yeah, so basically that's what you'll be looking at. So what data did I work with? How did it look like? So I actually got data from the National Institutes of Health. The data sets were made available on Kaggle. Just got them onto my local machine and did a little exploration. I realized that the healthy classes, I had so much of that. And then I had 14 other different classes of the diseased state, right? So a number of them infiltration. That means we have some stuff which are not supposed to be in the chest of the individual. So I mentioned cardiomegaly. So we have some cardiomegaly states in the images I worked with, and a few others. Pneumonia, that's what COVID-19 causes, right? So we have a number of these conditions in the images that I work with. Now, the other thing about the images I used was that when you look at, so for example, over here, this is the situation where this image has been diagnosed of having a condition, cardiomegaly, and an infiltrate. So it's not like we have just one image that has a unique disease. No, we could have just an individual having or being diagnosed of several diseases. So when I looked at the number of combinations that are available, I realized that I had a total of 839 diseases if I look at the permutations. So let's say infiltrate plus effusion, or effusion plus atelectasis, or effusion plus nodule plus mass. So that number of combinations gave me a total of 839. But definitely that's not going to help my model, because the model will just be looking around all over the place and just get confused.
Are they related in like a tree structure? So you can have an infiltration which is caused by something else in there, or is it you can only have one of those classes?
Yes. So usually when you have a condition diagnosed as mass, it's also likely to be an infiltrate. Like it's more like the infiltrates becomes a universal set, and then we have maybe the mass being a subset, right? And you would have a number of them fitting in here and there and intersecting. Yeah. So yeah. And the images I worked with were, some of them were actually labeled, right? And it was labeled using natural language processing. And it was reported to have 90% accuracy. Well, even though I'm not so sure of that, because when I did my manual review of the images I had, I realized that some of their labelings were not so accurate. For example, this in the image was labeled as atelectasis, but this is not atelectasis. This actually could be cardiomegaly and infiltrate. Atelectasis is the situation where your lungs have collapsed. So you are not really going to see any lung markings or anything, but over here, at least we can all see the lung a bit pronounced in here. So yeah, that's just an example of a bad labeling. Yeah, and a few others, because of how low the power of the X-ray device they used was, you could actually do a misclassification. So since some of the images were with low power X-ray devices, you would see that there could be some solid masses, or let's say opacifications, that's to say white structures in the lung fields, which necessarily does not, it's not pathologic, but it's just because of the low power device that was used. So I identified a number of such images as well. But I decided not to exclude those ones because, of course, I would want the model to be able to generalize well enough. Yeah. And of course, in the first example, we saw the electrocardiogram electrodes. So that's an example of some of the artifacts that were in the images. Now, aside the fact that the images were labeled, the distribution was not really balanced. So I had a little demographics. I got the gender information and then the age. So this graph here shows the distribution of the images, right? So I just looked at the situation where we have the diseased state, and for the gender female, we realize that we just have a small percentage, right? And just a large chunk of them are the healthy ones, right? And if we look at the distribution amongst males and females, it wasn't so balanced. So over here, the female class is denoted as 1, and then the male class denoted as 0. So you would realize that we have a number of true disease states in the male class, but quite a negligible number in the female class. So the first task was to balance the distribution and make it look a bit Gaussian. Yeah, so that was the first thing I had to do, so that I would not end up just training my model with just one class and at the end have it being biased. The next thing I did was to augment my data, because I had a total of 7,000 images. So I decided to do some data augmentation, and that helped me increase the training data to 15,000. I did a 315 rotation. Yeah, even though literature has said that when so much rotation was done on the MNIST data, they realized that the data sets at a point lost their labels. But it's quite interesting that a number of research articles I sourced did so much huge rotation. I saw 2 articles that did 300 degrees rotation, and I saw one that compared 120 degrees to 140 degrees. And it came out that the 140 degrees had better performance in terms of the accuracy. Yeah. So for my task, I did a 315 rotation, well, partly because of those articles I sourced. Yeah. And then I did a 10% width shift and then a 0.1% height shift. This is just to help me increase my training data and also help improve the model generalization. So I did the model training on my local machine. It's a 12 gig RAM quad-core CPU, not so much processing power. So what I did was, for each, let's say, model I decide to train, I just limited the number of epochs to 10, right? And then, so if after 10 epochs, I would review and see how good that model is performing, right? So if I realize that, no, this model seems to be doing some great job, then I would increase the number of epochs. Yeah. So I first started with a very simple baseline model. I got motivation from the VGG11 architecture, but I did a little tweaking. So I just reduced the filters. The VGG11 filters were quite huge, 128, 256, but I just used very low ones just because this was a first shot at the data sets. So just wanted to keep everything simple and see how it performs, right? And I gave it an input shape of 224 by 224 on the grayscale. And I did a 3x3 kernel convolution. And at the end of 10 epochs, I had a 0.55 validation accuracy. Not so good, might just be doing some guesswork in there. But yeah, this was just a simple module. So I moved out to explore some transfer learning stuff. I looked at the VGG16 architecture and used this as an integrated feature extractor. So what I did was I just built a new model. Yeah, so this is the architecture of the new model I built. I just fitted that at the output of the VGG 16, right? So the fully convoluted network at the end of the VGG 16 architecture, I replaced that with global average pooling and then some batch normalization. And then finally, I did a dense network and then my final output layer, right? So what I did was I froze the layers of the VGG 16 and just made the its layers as an extractor. So I was just trying to extract some features from the X-ray images, and once those are extracted, I would make that as an input to my new model that I built here, right? So I just replaced the bottleneck layers with an average pooling one and then did some dropout. So after 10 epochs, I had 0.62 validation accuracy. Not so good, but well, yeah, performed
Did that
better
help
than.
with the speed of the training at all?
Yeah, so in actual sense, I realized that the speed of my training reduced. Now, I had increased the input shape to 512 by 512. Just wanted to mimic the conditions under which the VGG 16 itself was trained. So, and also I was alongside just trying to do some hyperparameter tuning. So the simple baseline model I did was on the grayscale. This time around, I used an RGB one, and on the simple model, I did 224 by 224. This time around, I decided to increase it to 512 by 512, and it really took some time. The speed reduced actually, yeah. So I moved on to a bigger network, the DenseNet 201. Now, for this one, I used this as a weight initialization model. So its layers I did not freeze. I just took in the ImageNet weights, the ones I was trained on, and used them to initialize my weight, right? And I retrained all the layers afterwards. So the first epoch, I initialized the weights using the ImageNet weights and subsequently trained all the layers. And after my 10th epoch, I performed better. This model performed better than the VGG 16. So it gave me a validation accuracy of 0.65. So then I decided to move on with the DenseNet 201. And I increased that to 25 epochs because it passed my first 10 epochs threshold. And so now I increased it to 25 epochs. And at the 23rd epoch, I got a validation accuracy of 0.72. So I did a checkpoint right there. So I decided to plot a graph just to see how that was performing. And on the loss, I could see that, well, yeah, the model was learning. It's actually learning because I could see a general decreasing trend right here in terms of the loss value, and that was a good sign for me. And this increasing, that's a validation accuracy increasing right there. So that was actually a good one for me. So I decided to increase the training, the number of epochs, because at this point seemed a bit interesting. That's around the 25th epoch. I could slightly see some divergence occurring. So I was wondering, could it be that this is just a minimal divergence, or my model is beginning to overfit? So I just decided to increase that to 30 epochs. And after the third epoch, the validation loss and then the training loss begins to diverge. And looking at how the divergence it's occurring, it's a bit interesting to me. Now, the first query I had was, could it be that I do not have enough training data, or could it just be that my model is basically just overfitting? And or could it be that I would have to do some more rigorous augmentation? Could I just explore some more, let's say, rotation, or do a few shifts here and there? Could I just flip left or flip right? But I just decided to hold on with that and move on with the one I checked, where I checked points. That was a 0.72 validation accuracy. So I reloaded the weights of the model when it gave me the 0.72 accuracy, and then I plotted the classification report. And so right here, this trend line just shows what a random guessing would normally do. Just either say, oh, okay, so this is diseased, this is healthy, just guessing randomly. But with my model, I had a 0.77 AUC. And I think, well, yeah, compared to the random guessing, that is doing some good job there, well, at least on a low-powered processing computer. Yeah. And the interesting thing here, since it's a medical task, is, so for example, if I would want to say deploy this model as a first step in screening some medical images, then I might be interested in the recall and precision metrics, right? So I have a recall here of 0.79 and then a precision of 0.74. So basically what I'm looking at is, if out of, let's say, so much positives, how much positives are my model predicting right? And that is what is interesting if we're looking at deploying the model for a screening purpose. So in a large population, we are interested in, let's say, catching all the people that are actually positive in the population. So if it's a COVID-19 situation, you will quickly want to identify people who have the disease and quickly take them out of the population and isolate them. So the model should be able to at least get all the positives, right? And that is giving me a 0.79, right? Not so bad, moderate performance. Yeah, so I moved on to do a graphical user interface. I built a graphical user interface to see how my model would interact, right? So getting out of the Jupyter notebook, how would this look like? I built this using Tkinter, and I made it a Python executable script on my Ubuntu. So I'll just run that as a demo, right? So just trying a few things here, right? So what I just built a simple user interface, and what that does is it allows a user to upload an image, right? So it's ready. So this is a very simple user interface, right? And you have the option of uploading an image. So you click an image. For the purpose of the presentation, I just got a few images online, right? So, and then, so I searched healthy X-ray image, and then I labeled it healthy and just did a double check with my user interface and with the back-end model, right? So if you can clearly see this definitely should be a healthy chest X-ray image. We can see the dark region, that means this line field here, the right line field, is translucent, and that is expected because we expect this to be filled with air. This should also be filled with air. We have our heart shape, well shaped. We have the aorta rightly centered. We have the trachea well branched here. So I expect this to be a healthy. So this actually is a healthy chest X-ray, and I expect my model to classify it as such. So once you just click on the upload image button and you click classify image, takes just a few seconds, and it should give you so it classifies this correctly as healthy, right? So we could just try another one. Okay, let's look at this that I've labeled as diseased. Okay, so definitely this is diseased. I can spot some infiltrates here. Then classify. So diseased, right? So I could just search, let's say, randomly online now, and let's say X-ray chest images, right? Just to see if my model sees some very foreign. So let's see one that is so clear for everyone to just. Okay, so let me say diseased. Let me say diseased. Okay. All right. So something like this. Yeah. So this is very clear. This is a clear. So let's say XRR, right? So I save that, and then I launch my GUI, then upload an image. So this, right? So this should be classified as diseased, right? So it says this is healthy. So that means that the 0.79% validation accuracy, that would say that out of 100 images, 21 of them would be wrongly classified. So this is a situation where I have a wrong classification. Well, partly because this might be confusing to the model because it kind of sees the dark lung fields here and here, but right here, because of the breast tissues, it's a bit confused, as in, should this be classified as a diseased state or should this be healthy? Now, this I would say is diseased because of the heterogeneous opacifications. So the model got this wrong right here. But let's see if we get one that is so obvious, and let's see how the model behaves on that. So something like this. No, I think that's the same image. Okay, something like this. Okay, so these are just the points where the blood vessels meet with the aorta. So that could be a bit ambiguous. So, okay, I think I saw one. Okay, this. Save images. So, ray 1, 2. Save. So, launch. So, ray 1, 2. Okay. So, okay. So now this says healthy, and so it getting that wrong also. But let's see this. Okay, so this is clearly diseased. This is clearly diseased. So let's see how they'll cancel. So I need to classify this. Okay, so it says this is diseased. And then let's see another one here. Okay, so this is cardiomegaly. The heart is so enlarged. So this is also diseased. This is a cardiomegaly situation, an enlarged heart. So let's see. So it gets that also. Then let's just try one last one and see. Okay, so this, I can see a mass here. the heart is not well pronounced. I can see a little infiltrate here. So let's see, diseased. Okay, right. So yeah, that's how the model performs at the moment. And then let's see. So what can I do? Next steps. Annotate the images and retrain the model. So yeah, currently the model, it's not bounded. It's just looking at the image in general, and then it's trying to identify some features for it to label it as a diseased image or a healthy one, right? But then if with the current prediction that I'm doing, if I'm able to just get the ones that the model is correctly classifying and then plot bounding boxes around the diseased regions and retrain the model, this definitely is going to increase the performance of the model. I could also look at parameter tuning, explore the image resolution, and do some further augmentation to see. The third one is still to leverage on transfer learning. I'll do what we call the standalone feature extraction. So what I can do is get a model that has already been trained on an image data, then let my raw images, give my raw images as an input to this model, right? Then it does features extraction. Then I now pass these on as input into my new model. And that could also be one way of improving the model. So yes, this is still far away from perfect, even though moderately good, but I could plot bounding boxes, do some parameter tuning, and then do some feature extraction. So thank you so much, and let me know your thoughts, and you can always shout a question at me. Yeah.